Hi, my name is Olaf Bierman, and today I'm going to be talking about a user interface I created. This is a class management system. So I implemented the interface in C++, and it's a prototype for the final system, but it shows most of the actual functionality of the final product. The main points I will be looking at here are the scope of the project and the purpose of my design, the main tasks which are supported by the interface, and the design rationale I followed during this process. Next, I will be looking at the walkthroughs that I performed with low fidelity prototypes in order to evaluate the interface. I will also be discussing the implementation technology I used, and finally I will show some screenshots which will illustrate the transformation from a simple sketch prototype to an actual functional prototype. Okay, so the scope and purpose of my design. The class management system I implemented is designed to manage students enrolled in a college or university course, as well as grades for different students on assignments and tests within each course, and the waitlist for the course. The users of the system are instructors in a university, but this is obviously a very varied group which is difficult to narrow down exactly and is likely to change over time. The settings of use for the system are three main areas. This is within the classroom, in the instructor's office, and at their residence. The main tasks supported by the system are adding and removing students from the gradebook as well as from the waitlist, looking up students in the gradebook by student number, viewing the entire gradebook, which includes sorting the gradebook, and summarizing data. Finally, the task of clearing the gradebook is also supported. This saves the user the trouble of manually having to clear grades, say at the end of semester. Okay, so the design rationale I followed during the development of the prototype focused on usability. There are three main areas of usability I looked at. These are effectiveness, efficiency, and user satisfaction. Effectiveness means that the outcome of each task should be as close as possible to the user's actual goal, and they should be able to complete the task. Efficiency means that the amount of energy and time and other resources that the user must expend to perform the task should be as little as possible. Finally, user satisfaction here means that the comfort and acceptability to every stakeholder must be maximized. So stakeholders here, in terms of primary stakeholders, are the instructors who are actually using the system, as well as the secondary stakeholders who are the students who are directly affected by the system, but there are also others who are tertiary stakeholders who are indirectly or directly affected by the system but are not actual users of the system. Okay, so in order to evaluate my design, I used the design walkthrough approach. This was very useful because it allowed me to see usability issues within the design before I even moved on to implementation, which saved a lot of time and effort in the long run. This type of evaluation approach can be used at any point in the software lifecycle, before you even have any kind of working system available. So the type of walkthrough I performed is called a task-centered walkthrough. To do this, I've started by creating personas, which are essentially imaginary users that represent the different subgroups within the main user group. For each persona, I listed their skill level with computers, cultural background, language barriers, and any other factors that might affect their use of the interface, such as disabilities. So after creating the personas, I also created concrete task examples for each. So a concrete task example is an imaginary situation in which the persona uses the system to perform the different tasks which it supports. To find the actual usability problems, I broke each task down into different steps. So I started at the beginning where the user forms their goal and move towards the end where they achieve these goals. I then summarized these steps and added them to a table with cells with room for comments next to each step. So this would be used to actually perform the walkthrough. So during the walkthrough, I looked at each of the different concrete task examples, and for each of the steps in these tasks, I asked 3 questions. Does the user have sufficient knowledge to actually do this step? Is the action believable? And is it motivated by their goal? So for any step, if I had a no answer or there was some other cause for doubt, I marked the step and wrote a comment next to it to explain what was wrong. I used these comments later to address these issues in my design. Okay, so next I will look at low fidelity prototypes. This is actually a general category that includes different kinds of prototypes, which are simple sketches, storyboards with annotations, which are a bit more advanced but still pretty simple, and animated prototypes which allow real interaction. So the advantage of using any of these methods within the low fidelity prototype category is that they allow you to see the different steps within each task before you even have any kind of working system. And at the same time, you can find usability problems and even test the effect any changes you make based on what this will do to your system. So I chose the simple screen mockup approach using Mockup Builder, which can be found at mockupbuilder.com. And I used these throughout the task-centered walkthroughs as a guide to help me see what each step would be for the different tasks and to notice the potential problem areas within each task. So after summarizing the results of the different walkthroughs, I had a much better idea of what I needed to do to increase usability of the system. So before I even started coding anything, I already had a lot of the problems worked out. I didn't waste a lot of time doing this after implementation. So, and the other thing is, these prototypes offered a good starting point and a guide throughout the implementation process to help me see how I would do things like positioning widgets and sizing different elements and handling errors, handling input data, all of these things. So this is an example of what the prototype I use looks like. As you can see, it's very simple. It just gives you a rough idea of where you will position your elements and size them. So the important thing here is to notice here is that the prototype is not a polished product. It will be thrown away. So you can make changes easily and quickly without worrying too much about how they will look, just to get an idea of how this will affect your system. Alright, so moving on to implementation, I used Microsoft Visual Studio 2017 to implement the product in C++. I used this IDE for editing, linking, compiling, testing, and debugging, so pretty much everything. So my main focus was to create a working prototype as quickly as possible. So I focused on boundary classes. I didn't really create much in the way of entity and controller classes, although I did create some, but these mainly just return test data, which can be used by the boundary classes in the interface. Overall, I found that the object-oriented paradigm was very useful here. It allowed me to use features like inheritance and polymorphism to reuse as much of my code as possible, as well as abstraction, which meant that I didn't have to think about too many details at once. So I could create a base class for many of my components and then derive from this base class. So for example, I had a base class called task component, and I derived from this for many of my individual specific components. The components could then specify their own behavior as well as how they should be painted. But in many cases I could just use a lot of the code in the base class, and I didn't have to rewrite anything, or very little at least. Polymorphism was useful because I could treat any instances of classes deriving from the base class in a general way. So for task component, I could treat all task components in the same way in other parts of my code. So where a task component needed to be displayed, for example, within a window, I could just say task component instance of pointed to an instance of a task component. I didn't have to know ahead of time exactly what type of task component it would be. One of the things which I found most useful while developing this interface was the Juice application framework. This is a cross-platform framework which allows development for Windows, macOS, Linux, and mobile platforms. It handles a lot of the low-level aspects of interface development, which saves a lot of time. This includes the rendering of the windows via OpenGL context for each windows, and calls to the platform-specific window manager, as well as event handling, multi-threading, and the look and feel of each window. So this allows you to ensure consistency across the different application windows. It also offers pre-built widgets which can be customized or used as is, and the ability to create your own widgets by deriving from the base classes which represent components within the interface. So for example, there's a base class called component, and you can derive from this to create different buttons and any other kind of element in the interface, and you can create listeners which handle events on each component. The main drawback I found with this framework is that it requires a somewhat restrictive license to use, but the license is free, at least for personal and educational use, but for commercial use it is a paid license. But with a license, a view of the source code for the framework is given, so this is very useful for determining the efficiency of different modules and when deciding how to derive from the base classes and override existing methods within these classes. It's useful to be able to see the source code, see how these methods were implemented in the first place in their base classes. I will finish by showing some of the screen mockups for the user interface, followed by the actual implementation in the system. This shows the transformation from simple sketches to an actual working implementation. It also shows the changes I made based on the results of the walkthroughs. So here's the initial screen which users see when they open the application, which shows a list of courses being managed. And here is the actual implementation of the screen. This is just test data which is used to simulate the final system. Here's the prototype for adding a student to the gradebook. And here's the actual implementation of the sketch. So as you can see, the layout for the different components is very similar. And here's the prototype for the gradebook. And here's the implementation of this prototype. So the layout is very similar, but I also added some features here, such as the ability to sort the gradebook. Also a tip section here, which gives the user help in using this table. It tells them about how to sort the table, and also that they can drag columns around in order to rearrange them. The table can be sorted both ascending and descending. And here's the aggregated data for the grade average for the course, as well as the class size. Now here's the prototype for the waitlist. It's similar to the gradebook, except that obviously grades aren't shown and only shows name, student number, and the position of the student on the waitlist. The implementation follows a very similar layout, and it shows the number of students on the waitlist. Finally, here's the prototype screen for clearing the gradebook. The important thing here is that the user should be asked whether they want to continue or not, because this is a dangerous task which erases all data from the gradebook. So the user has to be absolutely sure that they want to continue and be given an opportunity to go back. And here's what the gradebook looks like after it is cleared. As you can see, it's completely empty. Now, moving forward, if we actually wanted to implement this system fully, there are three main areas which should need to be considered. The first one is to increase usability. This could be done by repeating the task-centered walkthroughs and applying the results of this, as well as performing a heuristic evaluation. Second, how will data be stored? Will it be stored locally in files or in a personal database for each user, or will it be stored remotely and integrated for different users in a remote database? Finally, we would need to consider security. Questions to ask here would be, does the system require password authentication, and is encryption of sensitive data required? And finally, will data be transmitted over a network? There are obviously other security questions that would need to be asked as well. I hope you've enjoyed this presentation, and thanks for watching.